From the moment we take our first steps to the grand dance of celestial objects, gravity shapes our universe. It is an invisible force, yet its effects are felt everywhere we look. Gravity is the force that anchors us to the Earth, preventing us from floating off into space. It is the force that dictates the motion of planets, stars, and entire galaxies. In essence, gravity is the force of attraction between any two objects with mass. The more massive an object, the stronger its gravitational pull. This means that a planet like Jupiter, with its enormous mass, exerts a much stronger gravitational force than our own planet. This is why Jupiter has so many moons and why it plays such a dominant role in the dynamics of our solar system. Despite its ubiquity and importance, gravity remains one of the most mysterious forces in the universe. Unlike other fundamental forces, such as electromagnetism, we don't fully understand how gravity works on a quantum level. What exactly mediates this force of attraction? What is the nature of gravity, and how does it fit into our understanding of the cosmos? Gravity's influence is evident in our everyday lives. When we drop an apple, it falls to the ground due to Earth's gravitational pull. This same force keeps us grounded and gives weight to objects. On a larger scale, gravity governs the motion of the moon around the Earth and the Earth around the Sun, holding these celestial bodies in their respective orbits. The tides we observe are another consequence of gravity. The moon's gravitational pull is stronger on the side of Earth closer to it, causing a bulge in the ocean water. As the Earth rotates, this bulge follows the moon, creating high tides. The interplay of gravity between the Earth, the moon, and the sun creates the complex tidal patterns we experience. Gravity's reach extends far beyond our solar system, shaping the structure of the cosmos. It causes galaxies to cluster together, forming vast cosmic webs. It drives the formation of stars and planets from clouds of gas and dust. Gravity is the architect of the universe, sculpting its grand design over billions of years. Understanding gravity has been a central pursuit of scientists for centuries. From ancient Greek philosophers to modern-day physicists, the quest to unlock the secrets of this fundamental force has driven scientific progress. Over the centuries, our understanding of gravity has evolved dramatically, with each new discovery building upon the work of those who came before. Our journey begins with Isaac Newton, who in the 17th century formulated the law of universal gravitation. Newton's law described the force of attraction between any two objects with mass, providing a mathematical framework for understanding the motion of celestial objects. His groundbreaking work revolutionized our understanding of the universe, uniting the heavens and the earth under a single elegant equation. However, Newton's law had its limitations. It couldn't explain certain astronomical observations, such as the slight wobble in Mercury's orbit. It also failed to address the fundamental question of how gravity acts over vast distances. To unravel these mysteries, a new theory was needed, a theory that would reshape our understanding of space, time, and the very fabric of reality. Our understanding of gravity, like many scientific concepts, has been a journey of discovery, refinement, and paradigm shifts. Long before the scientific revolution, ancient philosophers grappled with the nature of motion and the forces governing the cosmos. Aristotle, the renowned Greek philosopher, proposed that objects had an inherent tendency to move towards their natural place. He believed that heavier objects, by their very nature, had a stronger desire to reach the center of the universe, which he believed to be Earth. This led to the erroneous belief, which persisted for centuries, that heavier objects fall faster than lighter ones. While intuitively appealing, this Aristotelian view was fundamentally flawed. It would take the ingenuity of later thinkers to challenge these long-held assumptions. Despite its limitations, Aristotle's work laid the groundwork for future investigations into the nature of motion and forces. His emphasis on observation and his attempts to develop a comprehensive system of the universe, though ultimately incorrect in some aspects, inspired generations of scholars. It is through questioning, experimenting, and refining our understanding that we progress towards a truer picture of the natural world. In the late 16th and early 17th centuries, Galileo Galilei, an Italian astronomer and physicist, challenged the Aristotelian worldview through meticulous observation and ingenious experiments. Legend has it that Galileo dropped objects of different masses from the Leaning Tower of Pisa, demonstrating that they fell at the same rate, contradicting Aristotle's long-held belief. While the historicity of this particular experiment is debated, Galileo's experiments with inclined planes provided conclusive evidence. By slowing down the acceleration due to gravity, he was able to carefully measure the time it took for objects of different masses to roll down the incline. His findings were revolutionary. In the absence of air resistance, all objects fall at the same rate, regardless of their mass. Galileo's experiments not only debunked a long-held misconception, but also paved the way for a new understanding of motion and forces. His work emphasized the importance of experimental verification and challenged the prevailing dogma of the time. By carefully observing and measuring the world around him, Galileo laid the foundation upon which Isaac Newton would build his groundbreaking theory of universal gravitation. In 1687, Isaac Newton, an English physicist and mathematician, published his groundbreaking work, Philosophiae Naturalis Principia Mathematica, which laid the foundation for classical mechanics and our understanding of gravity. In this monumental work, Newton proposed his law of universal gravitation, a mathematical formula that quantifies the force of attraction between any two objects with mass. Newton's law states that every object in the universe attracts every other object with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. This elegant equation, F equals gm1 m2 over r squared, where F represents the force of gravity, g is the gravitational constant, m1 and m2 are the masses of the two objects, and r is the distance between them, revolutionized our understanding of the universe. Newton's law of gravitation was a triumph of unification. It explained not only why objects fall to the Earth, but also why the Moon orbits the Earth and why planets orbit the Sun. It provided a single, coherent framework for understanding both celestial and terrestrial motion, demonstrating that the same fundamental force governs the cosmos, from the smallest apple to the largest star. While Newton's law of universal gravitation was a remarkable achievement, it left some fundamental questions unanswered. One of the most perplexing was the concept of action at a distance. Newton's theory implied that objects could exert a force on each other instantaneously, regardless of the distance separating them, without any intermediary substance or mechanism. This idea troubled Newton himself, as it seemed to suggest a mysterious, unexplained connection between objects across vast expanses of space. How could the Earth know about the Sun's presence and respond to its gravitational pull without any direct contact? This conceptual difficulty, known as the action at a distance problem, would continue to puzzle physicists for centuries. Despite this conceptual challenge, Newton's law of gravitation remained incredibly successful in explaining and predicting the motion of celestial objects. It served as the foundation for astronomy and physics for over 2 centuries. However, the action at a distance problem hinted at a deeper, more profound understanding of gravity, yet to be uncovered, one that would require a radical reimagining of space and time itself. At the dawn of the 20th century, a young physicist named Albert Einstein would revolutionize our understanding of gravity, proposing a theory that went beyond the limitations of Newton's classical description. Einstein's theory of general relativity, published in 1915, offered a radical new perspective, suggesting that gravity was not a force acting at a distance, but rather a manifestation of the curvature of space and time itself. Einstein's journey towards general relativity began with his special theory of relativity, published in 1905. Special relativity dealt with the relationship between space and time, demonstrating that they were not absolute, but rather intertwined, forming a 4-dimensional fabric called space-time. This revolutionary concept laid the groundwork for Einstein's later insights into the nature of gravity. One of the key principles of special relativity is that the speed of light in a vacuum is constant for all observers, regardless of their relative motion. This seemingly simple postulate had profound implications, leading to the concepts of time dilation, time slows down at higher speeds, and length contraction, objects appear shorter in the direction of motion. These counterintuitive predictions have been experimentally verified, confirming the validity of special relativity. Einstein realized that special relativity, while groundbreaking, was incomplete. It did not account for gravity, which remained a mysterious force acting at a distance. He spent years grappling with this problem, seeking a way to incorporate gravity into his relativistic framework. His breakthrough came with the realization that gravity was not a force in the traditional sense, but rather a consequence of the curvature of space-time. Imagine a bowling ball placed on a stretched rubber sheet. The ball's mass causes the sheet to sag, creating a depression around it. Now, imagine rolling a marble across the sheet. Instead of traveling in a straight line, the marble's path will curve as it approaches the bowling ball, eventually spiraling into it. This is a simple analogy for how Einstein envisioned gravity. In Einstein's view, massive objects like stars and planets warp the fabric of space-time around them, much like the bowling ball distorts the rubber sheet. This curvature of space-time is what we perceive as gravity. Objects moving through space-time follow the curves created by massive objects, giving the illusion of being pulled by an invisible force. The trampoline analogy, while a simplification, helps visualize the concept of space-time curvature. Just as the weight of the bowling ball creates a gravity well in the rubber sheet, massive objects create gravitational wells in the fabric of space-time. The deeper the well, the stronger the gravitational pull. This curvature of space-time affects not only the trajectories of objects, but also the passage of time. Einstein predicted that time slows down in stronger gravitational fields, a phenomenon known as gravitational time dilation. This means that a clock placed near a massive object will run slightly slower than a clock farther away. This prediction of general relativity has been experimentally verified. Atomic clocks, which are incredibly precise timekeepers, have been flown on airplanes and satellites, and their readings have been compared to clocks on Earth. The results have consistently shown that time runs slightly slower at higher altitudes, where the gravitational field is weaker, confirming Einstein's prediction. Gravitational time dilation is a mind-bending consequence of general relativity, challenging our intuitive understanding of time as a universal constant. It arises from the fact that gravity warps both space and time, and this warping becomes more pronounced in stronger gravitational fields. Imagine two identical clocks, one placed on the surface of the Earth and the other in a spaceship orbiting high above. According to general relativity, the clock on Earth, being closer to the Earth's mass, experiences a stronger gravitational pull, and therefore time runs slightly slower for it compared to the clock in orbit. This difference in time, while incredibly small, has practical implications. The Global Positioning System, or GPS, which relies on highly accurate timekeeping to determine location, must take gravitational time dilation into account. The atomic clocks on board GPS satellites, orbiting at high altitudes, run slightly faster than clocks on Earth. To maintain accuracy, these clocks are constantly adjusted to compensate for the effects of general relativity, ensuring that our GPS devices provide precise location data. Einstein's theory of general relativity has been remarkably successful in describing the universe on large scales, explaining the motion of stars, galaxies, and even the evolution of the cosmos itself. Quantum mechanics, on the other hand, reigns supreme in the microscopic realm, governing the behavior of atoms, subatomic particles, and the fundamental forces of nature. Both theories have been incredibly successful in their respective domains, yet they seem fundamentally incompatible, painting vastly different pictures of the universe. General relativity describes gravity as a smooth, continuous curvature of space-time, while quantum mechanics describes the universe as inherently granular, with energy, momentum, and other physical quantities existing in discrete packets called quanta. This fundamental clash between the smooth, geometric picture of general relativity and the quantized, probabilistic nature of quantum mechanics lies at the heart of the challenge in unifying these two pillars of modern physics. The incompatibility between general relativity and quantum mechanics becomes particularly apparent in extreme environments, where both gravity and quantum effects are expected to be strong, such as the center of a black hole or the very first moments after the Big Bang. In these extreme conditions, the classical description of gravity breaks down, and a quantum theory of gravity is needed to accurately describe the physics at play. In quantum mechanics, forces are mediated by the exchange of force-carrying particles. For example, the electromagnetic force, responsible for light, electricity, and magnetism, is mediated by the exchange of photons, massless particles of light. Similarly, the weak force, responsible for radioactive decay, is mediated by the exchange of W and Z bosons. If gravity is to be unified with quantum mechanics, it too should have a force-carrying particle. This hypothetical particle, known as the graviton, is thought to be the quantum messenger of gravity. The graviton, like the photon, is predicted to be massless and travel at the speed of light. However, unlike the photon, which interacts electromagnetically, the graviton is predicted to interact only gravitationally, making it incredibly weakly interacting and therefore extremely difficult to detect. Detecting a single graviton would require a detector larger than the size of Jupiter, making direct observation practically impossible with current technology. Despite the challenges in directly detecting gravitons, physicists have indirect evidence for their existence. According to quantum mechanics, all particles, including force-carrying particles, should exhibit wave-particle duality, meaning they can behave both as particles and as waves. Gravitational waves, ripples in space-time predicted by general relativity, can be thought of as waves of gravitons, providing indirect evidence for the quantized nature of gravity. The search for a quantum theory of gravity is one of the most ambitious and challenging endeavors in modern physics. Such a theory would not only unify general relativity and quantum mechanics, but also provide a deeper understanding of the universe's most extreme environments, such as black holes and the Big Bang. While a complete theory of quantum gravity remains elusive, several promising candidates have emerged, each offering a unique perspective on the nature of space, time, and gravity. One of the leading contenders is string theory, which posits that the fundamental building blocks of the universe are not point-like particles, but rather tiny, one-dimensional, vibrating strings. Just as a violin string can produce different notes depending on its vibration, different vibrations of these fundamental strings give rise to the different particles and forces we observe in nature. String theory naturally incorporates gravity, suggesting that gravitons are just one particular mode of vibration of these fundamental strings. Another promising approach is loop quantum gravity, which takes a more abstract, mathematical approach to quantizing gravity. Instead of starting with a background spacetime, as in general relativity, loop quantum gravity suggests that spacetime itself is quantized, woven together from tiny loops of gravitational energy. This approach avoids the singularities predicted by general relativity at the center of black holes and the Big Bang, suggesting that spacetime has a granular structure at the Planck scale, the smallest possible unit of distance. The quest for quantum gravity is far from over. While string theory and loop quantum gravity offer tantalizing glimpses into a unified description of the universe, both theories face significant challenges. String theory, for example, requires extra spatial dimensions beyond the three we experience, and it has yet to make testable predictions that could be verified experimentally. Loop quantum gravity, while mathematically elegant, faces difficulties in connecting its abstract framework to the observable universe. Despite these challenges, the pursuit of quantum gravity continues to drive theoretical physics forward, pushing the boundaries of our understanding of the universe. New theoretical frameworks such as causal dynamical triangulations and emergent gravity are constantly being developed, offering fresh perspectives and innovative approaches to this fundamental problem. The quest for quantum gravity is not just about finding a single theory. It's about exploring the very nature of space, time, and the fundamental forces that govern our cosmos. In 2015, a century after Einstein first predicted their existence, gravitational waves were directly detected, sending ripples of excitement through the scientific community and beyond. This groundbreaking discovery, made possible by the Laser Interferometer Gravitational Wave Observatory, or LIGO, provided concrete evidence for one of the most mind-boggling predictions of general relativity and opened a new window into the universe. Gravitational waves are disturbances in the fabric of space-time, generated by the acceleration of massive objects. Imagine two black holes, locked in a gravitational dance, spiraling towards each other at incredible speeds. As they approach their inevitable merger, they release a tremendous amount of energy in the form of gravitational waves, ripples that propagate outward at the speed of light, stretching and compressing space-time as they pass. LIGO, with its twin detectors located in Livingston, Louisiana and Hanford, Washington, was designed to detect these minuscule ripples in space-time. Each detector consists of two perpendicular arms, each 4 kilometers long, housing laser beams that bounce back and forth between mirrors. When a gravitational wave passes through the detector, it stretches and compresses the arms by a tiny fraction of the width of a proton, causing a slight shift in the laser beam's interference pattern. The first gravitational wave detection, announced in 2016, sent shockwaves through the scientific community. It originated from the merger of two black holes, each about 30 times the mass of the Sun, located over 1 billion light-years away. This detection not only confirmed Einstein's prediction, but also provided the first direct evidence for the existence of binary black hole systems and their mergers. While general relativity has been incredibly successful in explaining the behavior of gravity on large scales, observations of galaxies and galaxy clusters have revealed a puzzling discrepancy. Galaxies rotate much faster than they should based on the visible matter they contain, suggesting that a significant amount of unseen matter, dubbed dark matter, must be present, exerting its gravitational influence. Dark matter, unlike ordinary matter, does not interact with light, making it invisible to telescopes. Its presence is inferred from its gravitational effects on visible matter, such as the rotation of galaxies, the bending of light around massive objects, also known as gravitational lensing, and the large-scale structure of the universe. While dark matter has yet to be directly detected, its gravitational effects are undeniable, leading to one of the biggest mysteries in modern astrophysics. Some physicists, however, have proposed alternative explanations for these gravitational anomalies. They suggest that instead of invoking unseen matter, perhaps our understanding of gravity itself needs modification. These modified gravity theories propose that Newton's law of universal gravitation and Einstein's general relativity, while accurate on certain scales, may break down on galactic and cosmological scales. One such modified gravity theory is modified Newtonian dynamics, or MOND. This theory posits that gravity's strength does not strictly follow the inverse square law at very large distances. In MOND, gravity's pull weakens more slowly with distance than predicted by Newton and Einstein, potentially explaining the observed rotation curves of galaxies without the need for dark matter. While MOND has had some success in explaining certain astronomical observations, it remains controversial. Dark matter, for now, remains the leading explanation for the majority of gravitational anomalies. While the search for a quantum theory of gravity continues, some physicists have proposed a radical idea that gravity may not be a fundamental force at all, but rather an emergent phenomenon, arising from more fundamental microscopic degrees of freedom. One such proposal is entropic gravity, which suggests that gravity emerges from the tendency of systems to evolve towards states of higher entropy, a measure of disorder or randomness. Imagine a hologram, a two-dimensional surface that encodes a three-dimensional image. Just as the information contained on the surface of the hologram gives rise to the illusion of a three-dimensional object, entropic gravity proposes that gravity emerges from the information encoded on the holographic boundary of space-time. In this view, gravity is not a fundamental force, but rather a consequence of the way information is organized in the universe. Entropic gravity is closely related to the concept of entanglement entropy, a measure of the entanglement between quantum systems. Entanglement, a bizarre quantum phenomenon where two or more particles become linked, sharing the same fate regardless of the distance between them, plays a crucial role in this perspective. Entropic gravity suggests that the entanglement between microscopic degrees of freedom on the holographic boundary of space-time gives rise to the force of gravity we experience in our macroscopic world. While entropic gravity is a highly speculative idea, it offers a fascinating new perspective on the nature of gravity and its relationship to quantum mechanics and information theory. It challenges the traditional view of gravity as a fundamental force, suggesting that it may be a macroscopic manifestation of deeper, more fundamental principles governing the universe. From the everyday convenience of GPS navigation to the groundbreaking possibilities of space exploration and medical advancements in microgravity, the practical applications of gravity knowledge are vast and continue to expand. As we delve deeper into the mysteries of this fundamental force, we can expect even more innovative technologies and applications to emerge, transforming our understanding of the universe and our place within it. Despite centuries of scientific inquiry and remarkable breakthroughs in our understanding of gravity, several fundamental questions remain unanswered. Gravity, while ubiquitous and familiar, still holds profound mysteries that continue to intrigue and challenge physicists today. One of the most perplexing questions is the relative weakness of gravity compared to the other fundamental forces of nature. Gravity is by far the weakest of the four known forces, vastly weaker than the electromagnetic force, the weak force, and the strong force. To put this in perspective, a simple refrigerator magnet exerts a stronger electromagnetic force on a metal paperclip than the entire Earth's gravitational pull on that same paperclip. This vast difference in strength suggests that gravity may operate differently than the other forces, or that there are aspects of gravity that we still don't fully understand. Another fundamental question is whether gravity is truly a fundamental force, or if it emerges from more fundamental principles, as suggested by theories like entropic gravity. If gravity is not a fundamental force, then what is its true nature, and how does it arise from the underlying framework of reality? This question cuts to the heart of our understanding of the universe's fundamental constituents and the laws that govern their interactions. The search for a quantum theory of gravity, a theory that can reconcile the principles of general relativity with the principles of quantum mechanics, remains one of the biggest challenges in modern physics. Such a theory would be a major triumph, providing a unified description of all known forces and potentially revealing deep connections between gravity, space-time, and quantum phenomena. The pursuit of answers to these fundamental questions drives ongoing research in gravity, pushing the boundaries of theoretical physics and inspiring the development of new experimental techniques. Scientists are exploring a wide range of approaches, from string theory and loop quantum gravity, which attempt to quantize gravity, to modified gravity theories, which propose alternatives to general relativity on cosmological scales. One promising avenue of research involves searching for deviations from general relativity's predictions, as these deviations could provide clues about the nature of gravity and the potential existence of new physics beyond the standard model. Experiments are underway to test gravity's inverse square law at very short distances, looking for any hints of extra dimensions or new particles that might mediate gravitational interactions. Astrophysical observations also offer fertile ground for testing gravity theories. The study of black holes, neutron stars, and other extreme environments, where gravity is incredibly strong, provides valuable insights into the behavior of gravity under extreme conditions. Gravitational wave astronomy, still in its infancy, has already revolutionized our understanding of black hole mergers and promises to reveal even more about the universe's most energetic events in the years to come. The development of new technologies, such as more sensitive gravitational wave detectors and telescopes capable of observing the universe in greater detail, will undoubtedly lead to new discoveries and further our understanding of gravity. For example, the Laser Interferometer Space Antenna, or LISA, a space-based gravitational wave observatory scheduled to launch in the 2030s, will be sensitive to gravitational waves of much lower frequencies than ground-based detectors like LIGO, allowing us to study a wider range of astrophysical phenomena, such as the mergers of supermassive black holes at the centers of galaxies.